now we'll talk about what we did yesterday. Yeah? So it'll be like a revision. Yeah? And tomorrow we'll talk about what we did today morning. So just to again revise what you did today, but do little different things. So what we will do over the next 1 hour or so, we'll finish this session a little earlier than scheduled because the lab sessions might take longer, is we will talk about experimental characterization of cutting forces. So characterization means many different things to many different people. For us it means describing what you're measuring, yeah? In terms of some parameters. Yeah? So that's how you characterize something, you describe it. Yeah? We'll talk about turning as well as milling, because we'll do both experiments that are planned. Are there any questions about anything before that, before we start, or we're all good? Yeah? Okay, no videos today, huh? So let's pay attention. Okay, this is you're familiar with already. You've seen this several times, you'll see it again. So I'll remind you, this is 3 inputs into making these process-machine interaction models and building these stability lobe diagrams. The machining process models. And what we're interested today is actually this. Yeah? I'll talk about that. There's dynamics, which we covered fundamentals of today, and tomorrow we'll do experimental dynamics for machines. And tool geometry, which is implicit inside our machining process models. Even the workpiece is implicit here, yeah? So we've not described that. So focus today is on machining, yeah? And identifying of these coefficients that we spoke about yesterday. They're called cutting force coefficients. If you remember, they have units of what? That's the edge, that's the cutting force coefficient, but there's also another coefficient which is the edge coefficient, which is not shown here, but we'll also identify that. Okay, so this is just the objectives of what we're trying to do. I think I've already motivated this. We need those coefficients for force prediction. We need them for input into our chatter models. And these coefficients also give you a sense of machinability of materials with a combination of tool and tool parameters. So it tells you how easy or difficult it is to cut something. So that is the objective. We'll talk about turning as well as milling and how to identify these coefficients. This you remember from yesterday, yeah? Or at least I hope so. In turning, so we had the tool, we have the chip. This is the clearance angle, that's the rake angle. This is your uncut chip thickness. Yeah? Light laga hai? And there are 2 forces acting on that tool. If you remember what they were, yeah? There is a, what component is this? We'll call this thrust, and this is feed. Yeah? So that's exactly what you're seeing there. Yeah? The total force is, this is thrust force, this is feed force, and even when there is no cutting taking place, there's always a rubbing force or an edge force, yeah? Or the ploying force, whatever you want to call it. So that's just what you're seeing there. 2 forces during cutting as well as during rubbing, so edge. The terminology might be a little different than what Dr. Chaudhary did yesterday, but essentially it's 2 components, thrust and feed. These equations you might remember from yesterday. Yeah? These are for orthogonal cutting. To predict these forces, you need the width of cut, the uncut chip thickness, which is h, and then it's just geometry and properties of the tool. So beta is your coefficient of friction, the friction angle. Alpha is your, I think alpha should be actually the rake angle. Yeah? So this is alpha, and let's make this gamma, for example. Yeah? Alpha is your rake angle, and you have also the shear plane angle, phi. Yeah? This is for orthogonal cutting. And tau s is your shear stress. So you can see both you can predict. Yeah? But what you need for this prediction is shear angle, which we still don't know how to get. Yeah? So there were two ways we described yesterday. One is you do this quick stop experiment. You stop it, you put a grid and you measure the angle. Or you try and use chip thickness ratios to get this information from that. But there is another method which we will talk about today, which is describing these forces differently. So instead of writing it as the cutting force and the edge force, you can write it in terms of its coefficient contributions. So that's KTC BH plus the edge times the width of cut. Similarly for the feed force. Now if you look at the similarity between this equation, this and this, you can see what your coefficients should be. Yeah? That's exactly what we're seeing here. Yeah? So KT is the thrust coefficient, Kf is your feed coefficient. And you can see we get this very simply from here. So what we're going to try and do is understand how to identify this experimentally without getting into chip thickness ratio calculations, without getting into shear angle prediction or shear angle measurement from quick stop experiments. Now you can see this is a combination of material, tau, as well as tool geometry. So each time you change the material or tool, this will change. Okay, and the best thing to do is identify it again. And it's not very difficult to identify, although there is a database of a lot of materials available, thousands of different materials. But it's for a specific combination of tool and material. Yeah? If you have a different tool and different material, identify it again. Not very difficult. This is orthogonal cutting. You have a question, Irana? Huh? You can ask now, it's okay.
No, this equation, whether the effect of, because normally also will play the role, whether that will be considered here or here in this equation I am not finding only the shear plane angle and the break angle.
Yes. So nose radius is not here, edge radius is not here. Yeah? There are a lot of things which are not here. Yeah? And in fact, this is why it becomes important to identify this. If you want to predict this, yeah, you will only use this information. And this does not have nose radius. Yeah? All this has is shear angle and geometry, friction as well as rake angle. There is no nose radius, there is no edge radius. So if you want to build a model which has all this information, it will become even more difficult. So what?
Because if I change the nose radius or something, FT will change and FF will change.
Yes. Yeah.
But here for the particular, here I am not finding it out.
So it's not in the model. And what we're trying to say is, maybe you don't need it to be in the model because you can identify these coefficients experimentally for a given nose radius, for a given edge radius, for a given tool geometry, and for a given workpiece material. So you identify it. Yeah? It's implicit inside this. We'll talk about how to get this. Yeah? Okay? Yeah.
The drawing force constants, they are proportional to your radius. Drawing action is a factor.
Yes, to a certain extent.
So it's incorporates that.
Yeah, but we don't have coefficients here for that. Yeah? As in no closed form solution for coefficients, because orthogonal cutting assumes sharp edge. Yeah? Yeah? These edge coefficients are absent. Even oblique cutting that we discussed yesterday, the assumption was no edge coefficients, no plowing. Yeah? But in reality it is there. Yeah? So that's why we're going to experimentally identify it. Yeah? Okay. Yeah? Alright, this is orthogonal. We also did oblique, if you remember yesterday. Yeah? So these are those long form solutions that Dr. Chaudhary was talking about. So you can see, this is again the three different forces. Here you had two. In the case of oblique, you will also have the radial cutting force, the third direction, or the axial, whatever you want to call it. Here you can see the forces that you will predict are function of rake angles in the normal plane, shear angle in the normal plane. Your I was your angle of obliquity, yeah? How much is the tool inclined? Your eta was your chip flow angle. Yeah? So all this becomes very difficult to model or predict. Again, we are motivating why we don't want to perhaps model, perhaps just experimentally identify what we want. So again, same logic, yeah, you can represent this differently using these coefficients, and you can identify what these things are. Yeah. So you can see where we are going, yeah, from orthogonal to oblique. Yeah. We've, instead of describing it using all these different geometric parameters, or shear angle, or normal shear angle, which I don't know how you will evaluate, we will just identify these coefficients which have all this information inside them. Okay? Alright? Yeah? Okay, so this is what we're going to do. We'll talk about how we're going to do it. So, you can do many different kinds of experiments. I think we were talking about orthogonal experiments yesterday. So typically, if you want to do orthogonal experiments to identify these, yeah, you start with the tube. Yeah. This is a thin tube. You have a tool here. This is turning. It's a turning experiment, and you're feeding the tube into the plane of the board. Yeah. So inside there, you're projecting it. So you first select whatever material you want to cut. Yeah. You set up this tube on the lathe. Yeah. Very simply. Importantly, your tool should have a zero inclination, yeah, flat rake, yeah, and no chip breaker. So you need to design this experiment very carefully, because to really get cutting which is orthogonal, where the chip flows nicely like this, yeah, is actually quite difficult. And for that, your chip has, or your edge also has to be very sharp. Yeah. So as low nose radius as possible. So you'll probably have to grind these tools specially, because you can't buy them any longer. Can you? Can a metal people? Do you make tools with no chip breaker, or for that matter, flat rake face or no inclination angle? No, right? You need to buy carbide inserts and then grind them off, yeah, and put them on a cutting tool and then prepare this setup. Very difficult to do. But you can. Yeah? So if you can instrument it, if you can set up all this, you can. Okay, so once you set up the material, you select the tube, you design this tool, yeah, specially. The next step will be you select range of cutting parameters that you most often will use this tool for. Yeah, so speeds, feeds, and so on. Because you normally know under what range of cutting conditions you're going to be doing certain applications, right? So aluminum, you will typically do high cutting speed, 300 to 500 or even 600, 800 meters per minute. Steel and titanium will be lower. Yeah? So you know that. So you set up your experiment for those kind of speeds. You measure forces. Yeah? How do you measure forces? We'll do that again today in the lab, but you use what we call a force measurement device, which is a dynamometer. Yeah? Has everybody seen a dynamometer before this? Yeah? Not our own students. Yeah? But people who are coming from elsewhere, have you used dynamometers? Yeah? No? So we will learn to use them today. Yeah? Okay. So this is the idea, as in how do you do all this? So a dynamometer just measures forces, yeah? And it measures forces not T and FF or tangential, axial, radial. It measures Cartesian coordinates, x, y, z. Yeah? That is why we did all those transformations in Cartesian coordinates, because that's what we measure. We can't see these FT, FF. Yeah? So if we'll measure cutting forces, we'll repeat everything for different feeds, yeah? Because that's typically what we do. Feeds as in different chip thickness. You change value of H. Sometimes you even change speed. You do this in one fix. In fact, I think we passed around sheets of paper. Yeah? Did everybody get a copy? So what we're going to do is turning as well as milling, and you will see it in the, I think the first page is turning, right? You see we're going to do experiments at two different speeds, and you're also seeing that we're going to change the feed levels, yeah? And there's a reason for that. We want to see how forces change, yeah? And so we repeat tests typically for different speeds. Yeah? If you're interested in seeing how this material behaves with different tools, you will also change tool geometry as necessary, and you will run a cutting force coefficient identification algorithm, which we'll talk about, which is the next slide. Yeah? So this is essentially the sequence of steps that you will follow to identify these coefficients. Very simple sometimes, but not always. Yeah? this has several advantages in doing orthogonal cutting. So this is a typical setup. I don't know if it's clear to everybody. This is the tool over here. This is the tube. It's aluminium. The dynamometer is the tool is being held in a dynamometer, so that's supported on a turret. And you're feeding it in this direction. So you're feeding the tool towards the left, and you're measuring forces as all three if you can, all three x, y, z axis. So your thrust force is going to be what is acting into this plane. So this is your thrust force, and your feed force is this. So that's what we're going to measure, but in x and y and z directions. These experiments are quite easy to do. If you can prepare a tube, if you can get a tool with a nice flat rake face, no chip breaker, this is very easy to do. And the advantage of doing this is, you saw those complicated equations that we're using, right, in oblique, is if you identify them in orthogonal cutting, you can transform them to oblique using a transformation. So you don't always have to do oblique cutting tests. So this is one advantage, because you can do these experiments, set up and try and measure. Okay, but with all good things, there are also some challenges. So there are also a lot of disadvantages with this. You need to specially prepare tubes and tools, which is not easy. We just discussed why. You need to conduct quite a different variety of tests, different speeds, different geometries, create a database and then transform them to oblique. And this is not really real. Orthogonal cutting is not really real. It's a lab setup, and it helps us understand the mechanics. But most cutting is oblique. Milling is oblique, drilling is oblique, turning is oblique. So it's not really representative. So what we instead want to do is oblique cutting coefficient identification. So what we do is we conduct a dedicated series of experiments using the tool and the material that we want to cut. So because you normally know what material you're cutting, and you normally know which tool you use for that material. So why not identify these cutting coefficients for that combination which you want to use? So that is what we will do. We know we want to cut aluminium. We don't know which kind of aluminium it is, but it doesn't matter, because we're going to characterize its performance in that one coefficient. We know which tool we want to use, because we know how to cut aluminium. It's special, so this is going to be a special tool with positive geometry, because you get better chip flow and chip breakage. And it's typically uncoated. So we'll use the real cutting conditions that we will finally do experiments or for your application that it demands. And what we do is you can see this, I think this is also in your table that we've given you. We'll run different experiments at different feeds, and we'll measure forces. So the only parameter we are changing is feed. We'll keep a constant depth of cut, one fixed spindle speed or cutting speed, and we'll change feed rate, and we'll now see how to identify these experiments. So this is the setup we have in a lab. This is a ACE turning machine. It's not very clear, but this is the dynamometer. It's got a tool inside. This is the aluminium workpiece we're going to turn, and you'll see more of that when you go there. So what we'll do is we measure forces. This is how forces typically look. It's turning. It's not periodic. It should be constant. So it's constant in the feed direction. There is some drift in the dynamometer. It takes time to settle. But so we measure forces, x, y, or FF, FT. You can rename them, and you create a plot. So what we are doing in this plot essentially is x-axis is your feed rate. You ran your experiments at different feeds. You measured forces for each feed value, FF, XC. So FT and FF, you measured these, and you just plotted, and you curve fit a line. That's what we want to do. Very simple to do this. You were asking how difficult it is to identify coefficients. To run 4 experiments takes 10 minutes. to fit this line takes even shorter. Yeah? So once you fit this, yeah, then the question is how do you get coefficients from this? Okay, so if you remember these two equations, yeah, what we want to get is KTC and KTE, as well as KFC and KFE. The 4 coefficients is what we want. And we have 4 experiments that we ran, measured thrust force and cutting force at different values of feed, made this nice figure. So what we want to do is first only consider the shearing components, yeah, which is because what contributes to cutting is only shearing. Yeah. Rubbing is always taking place, yeah, but chip formation is only because of shearing. So that is the major contributions, KTCBH and KFCBH. Yeah. And we can read them from the slope of this graph. The slope is your coefficient. Very easy to do. Yeah. So that's what. Sorry? No, so there are many different models. This is one model where we fit a straight line. There are other models called the Kienzl model where you can fit exponents, which is actually more real. Yeah? But if you're doing it for a given set of cutting parameters, this works best. It's easiest to do. Yeah?
This is I will conduct for just for example, if I do a machining of MS, the range will be the 70 to 120 or 70 to 150 the speed. For during my testing, maybe I will assume that 70. Here the only parameter variation is the field. Maybe at the customer place, suddenly we can change the cutting speed.
Yes.
But the KTC or KFC value, the constant will it be same, or if I am varying the cutting speed,
It will be different. Huh?
then I have to.
So you see the sheet that you see the sheet that we have given you, right? There are 2 values of cutting speed. Yeah?
But in between, okay,
You average it. Yeah?
300 to 400.
Yes.
In between, I want maybe.
So no, you can average it because anyway you are averaging. Yeah? All this is an approximation. Yeah? It gives you some idea. Yeah? Yeah? Otherwise, you are in the dark. You don't really know how it is going to behave. Yeah? So typically, you take low speed, high speed, yeah? And maybe you can even take in the middle. Yeah? And you measure in all 3 parameters, and you create a nice model, average all 3, and that's the coefficient you use. Yeah? Yeah, we're coming to that. Yeah. Okay. So, so shearing components we know we can get from the slope, but how do we get edge coefficients? Yeah? So when h equal to 0 is what your edge coefficients are. For this example, you can see it from here. Yeah. This is the equation of a straight line. Y equals to mx plus c. M is your slope. Now your slope you need to normalize for your chip width. In this case, your chip width is 2 millimeter. You divide that by 2, you get KTC. 1484 divided by 2. Very simple. So, is it correct? I've written it wrong. Okay. And this is nothing but your y-intercept, yeah? Your edge coefficients. Now you can repeat this experiment for a different set of cutting speed, for a different tool if you want, with different geometry if you want. You can change feed rates to see what you want, and you will see that it does not vary so much. So this gives you some. This is aluminium, so we know these values make sense. Yeah? And this is very simple to do. Yeah? Any question?
Small edge. Value small edge.
Small edge.
Edge.
Yes.
Value means
14 and 13. Yeah?
edge. Small edge. Alphabet.
Small h. No, h is changing, no? H changes from 0.05 to 0.125. H is changing, so that's the parameter you're changing, yeah, to do these experiments. Chip thickness or feed. Yeah? Okay, this is for oblique. This is still very easy to do. Milling, what will you do? Because these are very easy to, you can see slope is this, right? But milling, we know we have periodically varying coefficients. Entry angle changes, it changes as a function of helix, changes as a function of immersion. So this is not so easy in milling, but it's still possible. Yeah? So let's see what we do in milling. Yeah? Oh, importantly, before that, once you get these coefficients, yeah, you can put them back into your force model and predict what the forces will be. So that's how you will validate. Yeah? So once you get coefficients, then you want to know what the forces are. Yeah? You predict forces for you change cutting parameters, you change feed rate, you change depth of cut, you predict what the force is. Carry out an experiment with the same parameters. See whether what you identify is valid. Yeah? Then you will know that these make sense. And that's typically how we use this. Yeah? Because once you identify these and you validate them with other set of parameters, then you know these make sense and you can store them in your database and use them for everything else that you want to. Force prediction, torque prediction, sizing the motor, sizing the spindle power, or chatter prediction in the later instances. Okay, so this is oblique. Yeah? Units are only for this. This should be different. Yeah? This is Newton per millimeter, edge coefficients. This is T, this is just a typo. Yeah? Okay, I'll correct that. Okay. Yeah?
This sir, and it depends on only V, not only motor.
What?
The spindle speed,
Yes.
you can change by either by motor
Hmm.
or by parameter V. Because the spindle speed depends on motor, step motor.
No, this is a
There
servo
also we
motor.
change.
No, this is a servo motor. Okay, servo motor you can change speed continuously. It's not the AC motors that you're thinking which has a fixed speed. Yeah? Is that what you're thinking? जो 1500 RPM है, you can only run at 1500 RPM, for example, right? If you want to change the speed of the motor, you have to change the motor. This is or a VFD, a variable frequency drive. This is a servo motor which allows you to continuously change speed. Because speed is a function of diameter. We are fixing cutting speed, V equal to pi dn. If you want to keep V fixed, diameter keeps changing, you keep changing speed. And because it's a servo motor, it's very easy to do.
So it should also depends on depth of cut.
है ना, B.
B is the width.
हाँ, so this is turning. H is already here. H is the parameter you're wearing. B is the width of cut. Turning में depth of cut is what? H. This is your depth of cut. Yeah?
But it is fixed in graph. It is
Yeah, but so you imagine turning. Huh? This is your tube, right? Okay, this is your tool. You advance. Yeah? Your feed is your chip thickness or your depth of cut.
But depth of cut is something like that. So, suppose I have 25 mm dia.
Yes,
I want to make it 24.8.
yes,
So it will be 0.1 mm depth of cut.
correct.
Speed
Yeah.
is different, sir. Speed is different from depth of cut.
So what is width of cut in that case?
Width of cut is,
What is width of cut?
that's why I'm confused.
No, so as in think of it, no. Forget the tube. Yeah? Normal turning, you're turning a bar. Yeah? So this is how much you're in contact with. You move one, so say your feed is 0.1 millimeter per revolution. So per revolution of this, you move the tool by 0.1 millimeter, right? So this is one dimension. The other dimension is how much you're in engagement. Yeah? So this is the width of cut. Yeah? Width of cut, and you can consider this to be depth of cut.
Width of cut could be a thickness of the
How much you are in contact with the workpiece.
100%.
Yes, yeah. So that's what you're trying to say. So you have both parameters here.
Means width of cut and depth of cut is same.
No, no. Chip thickness and depth of cut are similar, and width of cut is a different parameter. Yeah? Okay.
Here for every different speed we have to do some new experiment to get the new case.
Yes.
If each speed changes, we have to redo it.
If it changes the lot, yes.
I would say because otherwise we say the forces are constant, it doesn't have any effect of.
No, no. Forces change with speed. They reduce typically.
Actually, when there is large change in speed, the forces do change.
Yes, they
We
reduce.
have to redo the thing for new.
Yes, you. Each time you change anything in the system, you need to do this experiment again. Other. Yes. Okay. This will change if you add lubrication. Yeah? Because we can't use lubrication because we have a dynamometer which does not tolerate fluid. Yeah? So we can't do these coefficient identification in wet conditions. But in wet conditions, forces are different. So there is a lot of variability, and this is what you have to appreciate. Yes, in any kind of modeling, these are the assumptions we are making. Yeah. So uncertainties in measurements, uncertainties in the model, and you have to appreciate this to understand why sometimes things don't work the way you want them to work. Because you cannot completely describe what is happening through equations. You have to make simplifying assumptions. Even in the experiments, we are making simplifying assumptions. Yeah? So that is important to keep in mind. Yeah? Okay. Can we move to milling?
Does it affect, let's say I have a taper turning.
Yes.
How you, does
So
it affect-
taper turning, the diameter keeps changing, speed keeps changing. Yes. Yeah. So, what is the question? Yeah?
So in that case, how to find this functions?
You change feed. You do one taper turning experiment. You change the feed, do another one. Change the feed, do another one.
No, our maybe this point of view is the effect of the spindle speed on the
Is already inside taper turning because it's continuously varying anyway. In taper turning, your spindle speed keeps changing because diameter keeps changing.
continuously we have to turn.
But your cutting speed is fixed.
Yeah.
Because that's fixed. Cutting speed V. Yeah? But spindle speed is a function of diameter. Yeah? That keeps changing. So
Yes. And another question is, let's say if there is a horizontal turning, or say VTL, and vertical
yes, okay.
and horizontal. So is there any difference in the cutting force
No.
if I use the same tool? Because usually what happens, the chip cutting is better when I keep the tool inverted.
In vertical condition.
Inverted, yeah.
Okay. In vertical condition.
In the horizontal only, inverted.
Okay.
The tip is facing downwards.
Okay. So gravity carries the chips away
Yes,
better.
yes.
Hmm?
So
That's
the
why
chip cutting
HMs
is better.
That's why horizontal machining processes are sometimes better because chip evacuation is better. If you do end milling or face milling on a vertical machining center and on a horizontal machining center, the mechanics are similar, but it's actually different because chip evacuation is different.
But in boring, the inverted has the better chip evacuation.
Yes.
That's not.
Yeah, so
I mean-
my point is exactly this. Yeah? If you want to really identify these coefficients, do them under the cutting conditions that are real for your application, because they will change. Yeah? You do them in turning, they'll be different. Yeah? You do them in boring because the boring tool is different geometry. Yeah? It will be different again. This is a function of tool geometry. Yeah?
Let's say if there is an ISO insert, so
Hmm.
I can use it for external turning as
Hmm.
well as internal boring.
Yes. Yeah.
Okay.
So if it's the same insert, same tool, same material,
Yes.
then it's okay. Then it should not change. Yeah? You can measure and see. It should not change so much, because what has changed? Tool is the same, material is the same. Nothing is different because this is only a function of those properties. Yeah? So, okay. Hmm? Very simple, but we'll move to milling. Yeah? Okay. Yeah. So this is our milling setup. Yeah? We have a vertical machining center. This is showing you a face mill. We'll actually use an end mill. It's easier to do. I'll show you why. Some things to keep in mind. Yeah? Again, you want to identify coefficients in milling. They'll be different than in turning for the same material. So we bought 2 blocks of aluminium, as in bars as well as blocks. We think it is the same aluminium, but it is not. Yeah? So if it is the same aluminium, it should have similar coefficients. Yeah? But coefficients we already discussed are a function of tool and a function of material. And tool in turning and tool in milling is different. Yeah? So coefficients will be different. So we'll do both turning and milling. Yeah? Things to keep in mind when you're doing this is because you have a dynamometer, don't make the workpiece too big. Yeah? Keep it small. This is not an ideal size. Ideally it should be smaller than this. This is very simple but important to keep in mind. Yeah? This is very expensive equipment. The kind of cutting parameters you will use to identify coefficients, keep them realistic. Yeah? So depth of cut as well as spindle speed. You don't want to go in the chatter regime. Yeah? Because you don't know where the chatter regime is, right? Because you're doing all this information to identify these stability diagrams. And because this coefficient is an input into that diagram, you don't know stable or unstable regime. So be conservative, because if you start doing cutting tests in the unstable regime, you will break the tool, damage the workpiece. These are just important things to keep in mind. When you're collecting information, so signal processing or gathering data, make sure you do it for at least a few complete revolutions of the cutter. Because if you saw yesterday, forces are periodic as a function of time, as a function of tooth angle. And we will average these forces, so make sure you have it over several revolutions, so you have good data. Very important. What we're going to do is fix the axial depth of cut. So here, milling axial depth of cut, you understand now? Vineet, is it? Yeah? Okay. So axial depth of cut, there is a radial depth of cut. In this case, axial depth of cut is 1 millimeter. Radial is going to be slotting. So 100% of the diameter. We'll create slots inside this workpiece. This is the feed. This is typical. This is actually again very conservative feed. We're cutting aluminium. You can easily go up to 0.3 or 0.4 millimeter per tooth. This is a cutting speed. This is a function of your tool diameter. In our case, we're going to use a 16 millimeter end mill. So this is coming from there. We're cutting at a fairly low speed, because we don't know where the chatter regime is, so we're being conservative. And this is what you will calculate the feed to be. So feed in millimeter per minute is feed per tooth into number of teeth into spindle speed. So that's what you get. So this is our experimental plan. Very simple to do. So what you need to do is gather data under these cutting parameters. So this is run number 1. Under these cutting conditions, you cut, acquire signal, save it. Run number 2, you do the same thing, acquire and save. Okay, so we will do. So this is what we look at. This is experiments that I was doing earlier in preparation for this lab. So this is run 1, run 2, run 4. So run 1 and run 4. All we've done is change the feed. And you can see how force levels are changing. So here the maximum force is about 190, 200 Newton. This is Y. Blue is X and Z is always very less. This is end milling, so there is no too much of a Z component. And this is for increasing the feed, you can see that the force component increases in all 3 directions. So this is what you can count how many revolutions. Each revolution should have how many peaks? 4 teeth. So it should have 4 peaks. So we're looking at least 2 full revolutions of the cutter. And what we will do, this is called the average approach. So you average the cutting forces over a number of revolutions. In turning, if you remember, your cutting forces are constant, right? Milling, it is not so. So to try and make them constant, we average them over a few revolutions. So the average in this case will be about 200 Newton in the Fy. Average in this case will be about 150 Newton, somewhere there. Okay, so average them, remember that. And for averaging, you need data for over several revolutions. Okay, there is a run out in this cutter. And that's why the force profile is a little strange. It's not like you expect it to be. But run out in end mills is very standard, very common. You cannot solve it, it's going to be there. You can try and minimize it with proper tool setting, but that's very difficult to do. We don't have the setup. So you measure the way you have, because that's how you're going to cut.
So evaluation is how from maximum to minimum.
Yes.
So how we can just 250 to 150.
Average, you take, you take area under the curve, sum it. Take the mean. In this case it's 250. You can either visually eyeball it, or you can take it, put it into a program, Excel, sum the values, or in MATLAB and say what the average is. So average in each direction, X, Y and Z. You need all 3 force components.
Even while reading also the dynamometer will read the if you are giving the values for that particular parameter, what is the speed of this thing, normally they will provide the average of this thing.
These are measured values. This is what the dynamometer is giving you. Dynamometer is not giving you average. This is what the dynamometer gives you. Yeah? You have to average it outside. Yeah? So processing cannot happen at the dynamometer, it has to happen outside that environment. Dynamometer gives you this force profile. Yeah? Yes, yeah. As you are measuring, you acquire data. Yeah? Okay, all right. So you remember yesterday, yeah? We had this really. You have a question, Irana? Huh?
There is a Whistler dynamometer.
Yes.
So which gives an average value. So this is the same.
No. If the dynamometer is giving you an average value, we are not using the dynamometer correctly. Dynamometer gives you instantaneous force value. Okay. If it's giving you an average, that means either it has inside it something that it can calculate an average. Yeah.
So
But
because we have some other CAE team also, they will,
okay.
We are using some software and calculation software and
Yes.
we take it as the highest forces and all.
Okay.
Analysis purpose and all.
For what?
Analysis purpose. The strength
Of the
that
cutter tool. Okay.
Then we will input those forces and all. Here, as you said, the average forces. So I got confused for the analysis purpose point of view.
The worst case situation.
Yeah,
But
worst
here,
case,
here we are averaging the forces over several revolutions. Yeah? For example, if I take instantaneous at this point of time, yeah, the force value is only 70 Newton. Yeah? But if I go to a little further time as it rotates, because chip thickness increases, it becomes 180 Newton. So which is correct? 180 also is not correct, even 70 is not correct. Okay, so that is the purpose of averaging over several revolutions. Yeah? So you get better data. Yeah? Okay. Yeah? So this is from yesterday. Yeah? If you remember this, the forces, Q is the subscript for x, y, z directions that we discussed yesterday, and phi p is the pitch of the cutter, and phi start and phi exit is the entry and exit angle. Yeah? So in case on, this is now slotting. Yeah? Yesterday we spoke about up milling and down milling. Yeah? So slotting is, this is your cutter and you're creating this slot. Right? So this is what you've already removed. Yeah? Cutter is rotating here, this is your first tooth, second, third and fourth. Yeah? And you're feeding the workpiece here. So slotting. So slotting, you can see the entry angle is 0 and this is your exit angle is 180 degrees. Yeah? So entry and exit. What we are doing is, this is the average milling force method, like I said. First you compute what the force is over one revolution. So that is what is here. Yeah? Also you are computing the force, so you are interested in the force only when it is in cut, yeah? Not when it is not in cut. Very important. Yeah? Okay, this is the analytical expression we saw yesterday. You can use this information, you can put this phi start and phi exit, and you can simplify this into forces which look like this. Yeah? So I'll go to the force expression since from yesterday. Perhaps you might better appreciate what we're looking at. Okay. So if you remember this, yeah, yesterday, we were looking at discrete elements. Yeah? We were looking how it changes the function of h. H changes as a function of phi and as a function of z. Yeah? And so this is at elemental level. You can sum forces over all teeth and calculate analytically. We did not discuss this formulation. We discussed only a numerical simulation yesterday. But if you pursue this a little further, you get a nice big closed form analytical solution, which we simplify, yeah, to get this. So we simplify for that entry and exit angle, and we get fx, fi, fz, which is, you can see, a function of radial coefficient, edge coefficient, tangential, edge, axial, and its edge coefficient. Yeah? So we simplified all those and we get something like this. This is from the analytical model. Yeah? NT is number of teeth. Number of teeth, A is the actual depth of cut, R, T and A are radial, tangential and axial coefficients. Yeah? And C is the cutting coefficient, shearing, and E is the edge. So we've skipped a lot of steps. Yeah? But what you do is, if you look at that analytical expression simplified for this geometry, you can reduce it to this. And this we're already measuring. Yeah? We measured Fx, Fy, Fz. Yeah? So you do some simple manipulation. Yeah? You fit, so like we did experiments in turning, we do them in milling. On the x-axis is different feet per tooth. On the y-axis is different forces that you measured, and you fit a line. Yeah? So you fit a slope. And this can be Fx, Q is the index for direction, x, y, z. Yeah? X, y, z. Yeah? You can see it's a function of, this is the average, this bar on the top represents averaged force. So we have the average force from there, we have the average force from here, measured. Equate these two and you get your cutting coefficients. So you see how we did that. We have an analytical expression, simplify it for this engagement, yeah? For slotting, you get this Fx, Fy, Fz, which is also represented like this, which we've measured, yeah? We've averaged that, and this is again an equation for a line. Yeah? Y is equal to mx plus c. From that you get coefficients. And this also helps explain, if you can see KTC, KRC, K, this should be A, yeah? This should be KAC. Why the Y component is always highest. Yeah? This is also, this green is Y, red is Z and blue is X. Yeah? Because the main cutting action is because of tangential force.
But
That is
axial is more than the x component.
axial is
Or
red.
one.
Axial is red.
Red one is more than blue.
No, it's lower. This value. So these are not magnitude values. No? So if, for example, at this feed, let's go back. Let's look at that figure. Yeah? Let's look at it here. So axial is Z. Z is the dark black line. Yeah? So it's actually just 25-30 Newton, whereas average for X is 80 Newton. Because this is an end mill. If it was a ball end mill, if it was an inserted end mill with a round insert, then the axial component will be very, very high. But this is an end mill. Okay, so we did this fitting and we got coefficients. Any questions here? So this is what we're going to do on the machine. Yeah? I think this is all that I have. Yeah? Okay, yeah. So like I said, our objective is to first understand how to do this. So this was to give you an overview of what we will do on the machine and show you really how simple it is to identify these coefficients. Turning is very simple, milling is a little, because you have to run this algorithm offline, yeah? But you can write a very small Excel or MATLAB script and you can fit this and then get these coefficients quite easily. Turning is very simple and we're in business. So good, we'll break early, yeah, because we have experiments might take time.